In this video, I want to think carefully about one idea. What is a vector? By the end, I hope this idea feels simpler and more connected. A vector shows up everywhere in multivariable calculus, so it's worth understanding it deeply. At its core, a vector represents both a magnitude and a direction. You can think of the magnitude as a length of the vector. Mathematically, we often represent the vector as an ordered pair or triple. For example, let's say let vector v equals 1, 2, which lives in two dimension, R2. Or let's say a vector u equals 1, 0, 1, which you can see lives in R3. So you can think of a vector as describing movement or change in space. It's also easy to represent a vector visually or geometrically on xy plane. Let me show you. So that's kind of thick, but it's okay. X, Y, 1, 2, let's say the origin 1, 2, 1, 2. So it's one component in the x direction and two components in the y direction. So one component and two, so here. So vector v points like this. This is vector v, 1, 2. As you can see, vector represent the direction. Or we can also represent the three-dimensional vector as well. Let me show you here. So x, y, and z. 0, let's say 1, 2, 1, and 2. X components is 1, 0 in the y direction, and another 1 in z direction. So 1, 0, 1, like maybe here. It's kind of hard to visualize exactly the three-dimensional vector, but you can kind of see the vector u goes 1 in the x, 0, and another 1 in the z direction. So this is the basic fundamental concept of a vector. We can add vectors or multiply a scalar to it as well. Let me show you an example. Mathematically, let's say a vector v, let v equals v1, v2, and a vector u equals u1, u2. Then if you add them up, v plus u, we just need to add each corresponding component. So we add v1 and u1 because they are x component, and v2 and u2 because they are a y component. So the result is v1 plus u1 and v2 plus u2. For example, let's say this vector v is equal to 3, 4, and this vector u is equal to -1 and 2. So we can just calculate it very quickly. So v plus u is 3 plus -1, which is 2, and 4 plus 2, which gives us 6. So 2, 6 is the result of the vector v and u. It's also the easiest to represent geometrically on xy plane. Let me show you. X and y. V goes 1, 2, 3, 3 and 4. 2, 3, 4. So 3 and 4. like here. This is v. And u is minus 1 and 2. Minus 1 and 2. So 2 in the x direction and minus 1 in the y direction. So here. So we already know v plus u is 2 and 6, but without calculating mathematically, we can also see the result by geometrical representation. So using, it's called tip to tail method, we can just put tip of the first vector and connect with the tail of the second vector, so it gives us this kind of vectors, and we just need to connect from the origin to the final tip. So this gives kind of 2 and 6, let's say. This is 6 and 2. So this is 2 and 6. So this is a vector addition. Alright, we can do a scalar multiplication as well. Let's use the same example, same vector we used for vector addition. So let's say vector v equals v1, v2, and let's say this equals 3, 4. The same. And let's denote the scalar as c. This is just a number, just a real number. And let's say this equals 5. So a scalar multiplication of c and v, we can just write it as c times v, which is equal to 5 times 3 and 4. And to calculate this, it's very simple. We just need to calculate each component by the scalar, which is 5 in this case. So 5 times 3 is 15. 5 times 4, 20. So the scalar multiple of 5 and 3, 4, a vector 3, 4, it gives a vector 15 and 20. We can also definitely represent this vector geometrically on xy plane. X and y. Since the number is kind of big, so let's say this is 5. No, let's say this is 10 and 20. 10, 20. So the vector 15, 20 should lies on, let's say like here, the half of the 10 and 20, and 20 in the y direction. So it should goes like this, 15 and 20. As you can see, scalar multiplication only changes the length of a vector. It's important to remember. It doesn't change the direction, but the length. 3, 4 only lies on the xy plane, like, let's say, this length. But when we multiply by 5, we can get much bigger magnitude of the same vector and the same direction. And the thing is, when we multiply by a positive number, it just stretches the length of the vector. But when we multiply a vector by a negative number, it also gives the same magnitude but opposite direction. This also reflects the commutativity of a vector. In multivariable calculus, change depends on direction. Gradients, vector fields, or directional derivatives, which we will going to cover later, all rely on vectors. So understanding vectors now will make these ideas way more natural and make sense later. That's all for this video today. We will build on dot products and cross products next time. So until then, let's keep things simply connected. Thank you.